So thanks everyone for coming to this very last session of the very last workshop of this long conference marathon. First talk is going to be by Jacco, who is going to tell us how we can avoid writing LaTeX ourselves in the future, I hope.
Yes, thank you all for coming to this last session. I know it's been a long day, or maybe a long week. So this will be a bit more of a practical talk. Yeah, my name is Jacco. I'm a PhD student at Utrecht University. And yeah, I'm going to talk about this little project I started, which I call InducTeX. And the problem I'm trying to solve here is that I write this little piece of Coq code with some inductive definitions. So in this case, it's the simply type lambda calculus with the syntax and the typing rules. And basically, I'm looking for a magic button I can press to give me the LaTeX inference rules. Yeah, so I looked around to see if this has been done, but I couldn't really find a good solution. So yeah, I decided to build something myself. But first, before I go into the how, I'll tell a little bit more about the why. So yeah, the main topic of my PhD research is this compiler, the Plutus compiler, which compiles a subset of Haskell into this lambda calculus. It's specifically system F omega mu, so it's a polymorphic lambda calculus with recursive types and type functions. But the Plutus compiler is a real compiler. It's implemented in Haskell. It's under constant development, and it's mainly used for compiling these smart contracts that we've heard about in the last session for the Cardano blockchain. So just a very brief, my version of the definition of a smart contract is a program that facilitates financial transactions between participants based on a predefined set of rules. And there's an obvious need for either formal or informal reasoning about the correctness of these smart contracts. As we've heard before, there have been numerous very costly bugs in this blockchain space. So what is interesting to think about is the deployment model of these smart contracts. So basically what happens is in this high-level language, in this case Haskell, the logic is written down, it's compiled down to this low-level lambda calculus, lots of optimizations happen, and this compiled version of the program is then sort of deployed as an entity in the blockchain, and participants who want to participate, they sort of have to trust that the logic of this obscure low-level program does what it's promising to do. So what we want to do in my project is to, given the source code or the supposed source code of that program, also a verifiable link or certificate that on the one hand relates the source code to the compiled code, and on the other hand shows that the compiler did not introduce any bugs in the process. So when you know you are looking at the actual source code, you can start doing this reasoning, and we've seen some interesting talks in the previous session on how you could do that. But this is more about enabling that kind of reasoning and making sure it's, well, trustworthy end-to-end in the compilation process. So the approach we're taking, we're calling it translation certification, and it's basically based on the well-known idea of translation validation. So what we're doing is we're treating the Plutus compiler in this case as a gray box system, and the compiler is, in this case, a multi-pass pipeline with optimizations, translation steps, etc. And yeah, what we do is when the compiler runs, we basically dump all these intermediate forms of the program, and then yeah, we build a system on top of this. So for each compiler pass that exists, we define a formal translation relation that sort of captures what each compiler pass should do. So this is like an inductive binary relation on ASTs. You could present it like a set of inference rules, and this will be relevant later on in the talk. But basically, it's yeah, a way of describing the specification of a compiler pass. And we do this completely independent from the compiler because Also, in this case, the compiler is not implemented in a proof assistant. The Plutus compiler is implemented in Haskell, but we can write these specifications down in Coq in this case. And the nice thing is that, for example, here, this is the specification of an inlining pass for a simply typed lambda calculus, but it's typically a lot shorter than writing down the actual implementation of an inliner, which may rely on some magical heuristics, on deciding which terms to inline, etc. But this relation captures all possible valid ways of inlining terms in the program. Okay, yeah, so like I said, we define these binary relations in the Coq proof assistant. And then the next step is that we implement a decision procedure. So that given a preterm and a post-term is what we call them, that are dumped by the compiler, we can decide whether they are indeed related through this specification. So then we have all the basic building blocks to build this translation certification infrastructure. And on top of that, we then prove that any related terms are also semantically equivalent for some definition of semantic equivalence. Now, so I briefly mentioned that we built this system on top of the actual compiler, and we call this system the certifier. So what it looks like if you have a run of the compiler here on the left, where on the top you start with the source code and you step-by-step translate to the low-level lambda calculus version. What we do is we dump the programs, and then we read them back into the Coq proof assistant so that we can formulate all the theorems, basically stating per pass that the specification is adhered to. Then we run all the decision procedures to actually produce all the proofs for those. And then we use the equivalence results to build one compact proof object, which basically states that the source code is equivalent semantically to the target code. Now, the point is that when a participant in the blockchain space wants to sort of participate with this compiled version of the contract, they can now look at the source code together with this proof and basically push it through the Coq kernel and get the approval that this is indeed the compilation we were talking about. And the nice thing about this setup is that we have a small trusted computing base. Basically, it's the Coq kernel together with all the definitions that make up this theorem that's being proved by the certificate. Okay, so let's get back to this first step of specifying these translation relations. So again, here's an example. This is the inlining I was talking about. So the judgments here take the form, they look a bit like type judgments. So it says gamma, under gamma, an inliner can transform term T1 to T2. In this case, gamma is not an environment of type assignments to variables, but it's basically all the lab bindings that are in scope. So it maps variables to their right-hand side as they were defined at a lab binding. And we can see the top two rules. They explain how a variable could be translated. So one case is that the variable is just untouched, nothing is inlined, and the other variable occurrence could be transformed into T when there is a term T prime in the gamma environment, and T prime can be recursively transformed into T. And there's a bunch of other rules, basically mostly congruence-like rules, and this neatly captures an inlining pass. Now, it's nice to look at these rules and explain them this way, but in practice, we implement them as a Coq relation. And okay, for the simply typed lambda calculus, this is still decently readable. But for example, in the Plutus compiler, the language is much larger, and these relations are much larger as well. And on top of all the specifications per pass, we have a formalization of the type system. We have a notion of type normalization. We have type equality. We have a big step operational semantics. So we have a lot of these inductive relations. Yeah, and so one of the things that we noticed is we don't only want to use these inductive relations to build this certified compiler on top. We also see them as the actual specification for the implementation of the compiler. So we want to use these definitions as a reference for the compiler developers, which may help them in discussions about the implementation or any refactorings or just informal reasoning about how the compiler is supposed to work. But yeah, these compiler developers don't always know about Coq syntax, so this is where the original idea came from. I want to typeset all these relations as some nice inference rules in LaTeX. Okay, so how do you use this little tool that I developed? Basically, first step, you specify your inductive relation. Second step, you provide some notational rules. I'm not sure if this is readable, but okay, I'll get back to the notational rules in a second. And then you run this little MetaCoq program, which then generates the LaTeX for you. So here you specify that you want it written to some file, and we run this print rules function that takes all the notation instructions and some other config. And finally, the last argument is the inductive relation that you want to print. Okay, so I think most of you here are familiar with MetaCoq, but it's a meta-programming system for Coq. And I'm not using any of the fancy meta-theoretical results that have been done in MetaCoq. I'm basically just interested in some reflection of the syntax. I want to inspect the inductive structure of inductives. And sure enough, if you look at the AST definitions in MetaCoq, you can see there's references for referring to inductives. There is some representation for constructors inside the inductives, which is basically just a list of names paired with the type of that constructor. And then there's even already a sort of pretty printing function, which takes a term into a string. So this seems like it's just connecting the building blocks and writing this function. So here's some code in the template monad that you can do. It quotes the reference of the inductive that you provide. And then it looks up, basically the constructors of that data type, and calls this pretty print rules functions at the last line. So, okay, that seems fair enough. Let's try it out. So here's my simply type lambda calculus again. At the bottom, I run MetaCoq run print rules for this inductive. What do we get? Okay, it's not great. There are some horizontal bars here. So, okay, it's at least printing rules. The point is, for example, it's including all constructor arguments. So, whereas you might want some implicit arguments, etc. And also, if you zoom in a bit, for example, here we look at this expression with cons. We have no notation like we're used to in Coq. Fully qualified identifiers, and if you look closely, this is just the first argument of cons, but it's a type argument, basically saying that it's the product of two types. So, yeah. And what's unfortunate is that in MetaCoq, it wasn't possible to access this notation information and information about implicit arguments and that kind of stuff. So yeah, we have to work around that in order to get some sort of reasonable pretty printing. So to do that, I introduced a few tiny set of combinators just to handle some strings. So for example, here at the top you see a few rules for the three constructors of the lambda calculus. So this says that if you see a variable case, when it's applied to a single argument, which is the name of the variable, you just print the name of the variable. But in the case of the lambda, you get three arguments, and you can combine those three strings basically into what you would expect in LaTeX. But also in here you can mention names of inductive types. So it's not just constructor names. So this is the actual type of the type derivations. And you can mention function names, etc. And to deal with, for example, implicit arguments, you basically just ignore some of the type. So for example, here you ignore the type argument. It seems like this double arrow thing is a bit magical, because on the left-hand side it has, well, it can have constructors which are not applied yet. It can have types, it can have functions. So how does that work? It's basically using this little quotation trick from MetaCoq. So between the percent signs, you can quote any term. So what we get here is basically this whole list of notations is just a lookup map for expressions to their predicting function. But yeah, we're basically using the actual notation Coq mechanism to define our custom notation mechanism, which is a bit funny. Let's see, then we have some extra configurations. So for example, we've seen that by default it would print all the premises, like all the argument types as premises. Well, we can just choose to, for example, not print any premises that don't have a dependent type, which is, at least for the example with the type system, is a decent choice. And then we can, again, implement this printing of rules in a more sensible way. And then we run it, and yay, we get the expected result, some nicely printed LaTeX. Okay, so I also looked a little bit into seeing if I could integrate this with existing documentation tools. So the obvious first candidate is CoqDoc. This is sort of the default documentation tool, but it basically just parses the source. It's very lightweight, but it doesn't really run any of the code, so it can't really compute my LaTeX representation. Then I looked into Electrion, which is a really interesting tool and much more recent. It's a collection of tools for writing technical documents that mix Coq code and prose, or also a literate programming toolkit that basically uses restructured text combined with Coq code. But most interestingly, it runs your Coq session and basically records intermediate proof states, all that stuff, including the messages that Coq produces. So it's a very interesting project, and I would highly recommend you to look at the GitHub page. It has a lot of nice examples and visualizations, but it did not yet have, well, printing inductives the way I want. So yeah, I basically just integrated that, and with a bit of MathJack's JavaScript hacking, it was possible to just print this inside the web page that Electrion can generate for you. So this is just a screenshot from the browser. Right, so there's some related work. There's this OT tool, which is a separate meta language for describing programming language semantics. And it can also print inference rules, and it even has a backend to produce Coq code. But this is a bit of the other way around. I'd rather have my definitions in Coq and just directly print them. There was an actual Coq to LaTeX tool, but it seems unmaintained. It relies on a custom parser, and it's only usable on Windows. And it also requires annotations on the source code, which looks a bit like this. And this was something I wanted to avoid explicitly. I would like to have my usual Coq definitions and then modularly or separately define the notations for printing. So some obvious next things to do would be to also pretty print simple ADTs as grammars in EBNF notation. It would be really nice if I could somehow reuse the Coq notation mechanism. And I have some ideas. I mean, this information must be available on the OCaml side, so maybe it could just be exposed in the MetaCoq interface. And some other idea would be maybe to generate, instead of generating a string in MetaCoq, just generate some isomorphic generic representation of an inductive data type, and then just use the normal Coq notation mechanism afterwards. I would also be interested in trying out this extractable template monad, where you can basically extract your MetaCoq code into OCaml, So that's just a bit more performance. Right now, for the larger relations I've tried, it takes a few seconds, but yeah, it's not great. So in conclusion, with this tool, you can pre-print inductive definitions that are readable for non-Coq users, and it also saves authors from duplicating their relations in tech. And yeah, it also keeps saving you keeping the definitions in sync. This is still very early development on this tool, so any suggestions or ideas are welcome. And thanks for your attention.
Yeah, thanks a lot for the talk. Do we have questions in the audience?
Hi, I was kind of curious. I mean, no, the Coq notation mechanism is quite strong. You can do a lot of hackery there, and you can get I think, a pretty good-looking ASCII art-ish version of your inductive definitions. If you use this kind of and maybe abuse this notation system. Did you try something like that before going for the much more ambitious version that prints out rules? Or because I mean the point is that you want something that's readable by people that can't read Coq code. But maybe with enough notation you can have something that's readable and that's maybe less difficult in terms of work than full-blown LaTeX support.
Right, so maybe it's possible, but I couldn't find a way to basically inspect the structure of an inductive definition. I know notations can be used for expressions or terms, but yeah, this is like a sort of meta construct that you cannot really inspect.
Okay, yeah. Oh, yeah. So you still need to keep the pipe and stuff, and that thing you can't do anything about. Okay.
Right. Yeah. Well, so unless this second option of generating some generic representation through MetaCoq, okay, you have an object, a term you can inspect and use some interesting notation for.
Yeah. Okay. Yeah. Thank you.
All right, let's thank our speaker again.